Morning, good afternoon, everyone. How are we doing? Questions while we wait? Good afternoon, everyone. Come on in. We'll discuss that momentarily. The number of attempts does not matter, as long as you get the right answer. We were looking at, well, I mean, it's still early. There are only 36 people here. Let's wait another few minutes. Yes, the music today was brought to you by Harmonium. A mythical band from the 70s. So popular. First of all, they only sang in French, but so popular that they were invited to tour California in the 70s. They have just released a symphonic arrangement of a lot of their songs. You can look that up. Questions while we wait? We were looking at inverses last time. Shall we take one or two examples? We are asked to find the inverse if it exists. Weather's fine, kind of cold. It's been minus 10 every day for the past, over the weekend for sure, for the past several days. Britton is asking, for word problems, how do you know how to construct the matrix? You don't. That's the thing. Don't be looking for shortcuts. Don't start a question with a preconceived notion that you need a matrix here. Instead, introduce variables for whatever the question is asking. Then, if you have a system of equations, then you can use matrices to solve that system. But don't try to go from a word problem directly to a matrix. That is terrible. That's terrible. You won't know if the constants should form rows or columns. And I mean, nobody knows. There's no way of telling. You have to set up first. Introduce variables, set up equations, and then move on to a matrix. Is everybody, well, first of all, you know what to do here. Is everybody following what's happening with GameStop in the US? How do we find the inverse here? You know what to do. You augment by the appropriate sized identity. Then you row reduce. GameStop, right? GME. On the New York Stock Exchange. It's crazy. They're squeezing the short position. It's I should have bought yesterday, but didn't want to get involved. But yeah. There's this hedge fund that was shorting the stock, trying to make it go bankrupt. And then people on Reddit decided to hedge against that. So people are buying and holding, and those who shorted are in a terrible position now. All right. So GME is the ticker for GameStop, New York Stock Exchange. Yeah, exactly. Well, they're forcing those who shorted to cover. I mean, well, yeah. Well, we'll see what happens with that, but I by the way, I don't own any stock in this, so, and you should probably not be taking any kind of financial advice from me. Let's row reduce this. Apparently there was some short interest on BlackBerry. Apparently some people are shorting BlackBerry. So maybe the same thing, I don't know. You know what to do. Absolutely. We did not do this question before, right? Am I correct here? Thank you. We'll use this 3 to get rid of that 3 by saying row 3 plus row 2 for row 3. And this plus this. Change this into a 1. We'll use that one to clear out the column. Change that 3 into a 1. Use that one to get rid of that one. And I mean, you know what to do at every step, right? This is not a surprise to you, right? This is just row reduction. Row reduction. The method in which you are experts at, right? So row 1 minus row 2. And finally, finish it up. 1/2 row 1 for row 1. So you have the identity on the left, and consequently the inverse is on the right. There we go. This is the proposed inverse. Let's check. Is this right? Have we made a mistake? Because you can check your answer. right? If we denote by A our original matrix, then A inverse is this thing over here. And we can check whether or not this is correct, right? Because if you multiply the two together, you should get the identity. So let's check. So here we're checking our answer. Always nice to check. Is this right? This times this. 4 over 3 minus 1 over 3 is 3 over 3, which is 1. An excellent start. Minus 1/2 plus 1/2 is 0. Minus 1 over 6 plus 1 over 6 is 0. Excellent. Minus 1 plus 1 is 0. 3 over 2 minus 1 over 2 is 2 over 2, which is 1. 1/2 minus 1/2 is 0. Looking good. Looking very good. 8 over 3 plus 1 over 3 is 9 over 3, which is 3. Minus 3 is 0. Minus 1 minus 1/2 is minus 3 over 2. Plus 3 over 2 is 0. Minus 1/3 minus 1/6, so that is minus 2/6 minus 1/6 is minus 3/6, which is negative 1/2. Plus 3 over 2 is positive 1. Excellent. Very nice. How are we doing? Questions? We're good? So we know how to find the inverse of any square matrix, right? It's the same thing. Do we want to do one more example? Do we want to do a 4x4? Or are we good with that? 4x4, or are we moving on? You tell me. You probably want to move on. 4x4, really? All right. Let's do a 4x4. Move on. 2 for 2. Tiebreaker. Who's gonna? There's actually a lot more for the 4x4. Oh, too late. Here we have this 4x4 matrix. It's too late to move on. I've already written it down. Let me make it quick by augmenting by the appropriate size identity already. Hopefully this will be quick. Let's use this one to clear out the column. So row 2 minus 2 row 1 for row 2. row 3 minus 3 row 1 for row 3, and row 4 minus row 1 for row 4. This minus 2, this minus 2, this minus 2, this minus 3, this minus 8, excellent. What do we want to do? Let's use this one to get rid of that 3. Row 2 plus 3, row 4 for row 2. And then we'll interchange row 2 and row 4. So this plus 3, this plus 3, that's going to be a 4. This plus 3, so minus 11. This plus 3 minus 5, 1. 0, 3. Let's use this 2 to get rid of that 4. Row 4 minus 2 row 3 for row 4. Is there anything else we can do? All right. I mean, I'm always looking for extra steps that we can do because it becomes tedious rewriting these matrices down, as I'm sure you have noticed. So 16 minus 11 is 5. This minus that times 2, so it's 1, 1 minus 2. Are these correct? Now we have no choice but to introduce fractions here. That is no, that's too bad, but that's where we are. So 1 over 5, row 4 for row 4. 1/2 row 3 for row 3. Yeah. I mean, you can do that. Nothing wrong with that. The problem is now you'll have fractions here as well, involving a denominator of 2, and then you'll be adding or subtracting denominators of 5, and it just piles up. If you hold off on that and use this 1 to clear out the column, now you just have one denominator to work with, denominator 5, so it's relatively straightforward. So let's use that 1 to clear out the column. Row 1 minus 2 row 4. Row 2 plus 2 row 4. And row 3 plus 8 row 4. See what happens. Row 1 minus 2. So that is a 3 over 5. Minus 2 over 5. 4 over 5. And minus 6 over 5. This plus 2 times that, so that again minus 3 over 5. 2 over 5. Minus 4 over 5. And finally 11 over 5. We're adding 8. So minus 15 plus 8 is going to be minus 7. Five minus 16 is minus 11. And finally 24 over 5. Finally, last row remains unchanged. So now we can divide by 2 with relative ease. Why don't we do row 1 minus row 2 while we're there? Seems like the thing to do here. I think we'll save a step if we do that. We get this minus this. This minus that. This minus that. Have we made a mistake? Can we repeat what is written in the first 2 lines? Here, 3 over 5, minus 2 over 5, 4 over 5 minus 6 over 5, minus 3 over 5, 2 over 5, minus 4 over 5, and 11 over 5. Are questions of this length going to be on the exam? Sure. It's a 72-hour exam, right? So it's not really an issue. Let's finish it up by using this one to clear out the column. Row 1 plus row 3 for row 1, and row 2 minus row 3 for row 2, and that'll do it. Getting the identity on the left, and consequently the inverse on the right. So this plus this, 12 minus 7 is 5 over 10, which is 1/2. This plus this is 0. 16 minus 11 is 5 over 10, which is 1/2. And this plus this is minus 5 over 5, which is minus 1. What are we doing? This minus that. So minus 6 plus 7 is 1 over 10. This minus that, minus 2 over 5. Minus 8 plus 11 is 3 over 10. And this minus that is a minus 1 over 5. Everything else remains unchanged. There we go. So here's the proposed inverse. I will let you check that this is right. I'll let you check that it's right. If it's wrong, then quite oftentimes you can kind of pinpoint where things went wrong, right? Sometimes it might just be 1 or 2 entries, and then you kind of see that something's going wrong, and then go back and fix it. Questions here? It's correct, thank you. Thank you for checking that. All right. All right, so, we've been doing inverses. I'm sure you're very comfortable with that. Interestingly enough, in the 2x2 case, we have a shortcut. We have a shortcut for finding the inverse of a 2x2. Only works in the 2x2 case. And there are no shortcuts for higher dimensional matrices. for larger square matrices, only for the 2 by 2 case. If A is the 2 by 2 matrix ABCD, and AD minus BC is not equal to 0, then A is invertible. In other words, the inverse exists, and the inverse is 1 over AD minus BC times D negative B negative C. Let's prove it. Let's prove it. It's not immediately clear. But we did prove last time that the inverse is unique. So as long as the product of this times the original one is the identity, we're good to go. Let's work that out, see what happens. Let's prove it. All we need to do is multiply these two things together. Then A is invertible. Invertible, meaning that the inverse exists. And A inverse is this. All we have to do is verify. All we have to do is multiply these two things together. That's all we need to do. If this gives us the identity, we're done. You know how to multiply matrices together. This times this. AD minus BC. This times that. BD minus BD. Well, that's 0. This times that. Minus AC plus AC. That's 0 again. And minus BC plus AD, or AD minus BC. And now if you multiply this matrix by this number, you know how to do that. You multiply every entry by this number. So you get AD minus BC over AD minus BC. That is easily seen to be 1. 0 times anything is 0, and 1 again. That's it. Absolutely. Thank you, Thomas. You get the identity, and that's it. That's the proof. These two matrices together, multiply to give you the identity. These are inverse. These are inverses of each other. I probably should not have erased that so quickly. I'll rewrite it momentarily, but let's use it to answer this question. We are asked to solve the system using the inverse. We saw as motivation for the matrix multiplication that you could rewrite the system as a matrix equation, right? This is -1, 2, -2, -1 times xy equals 1520. Or if you prefer, in general, a times some unknown xy equal to b. And motivation for the inverse then came along, and we noticed that if the inverse exists, and you multiply by the inverse on the left, you have a times a inverse times x is a inverse times b. If you do the same to both sides, equality is maintained. But a inverse times a is the identity. And the identity times x is just x. So you can actually solve the system, assuming that the matrix of coefficients is invertible. You can solve the system this way as well. Now, what this earlier claim told us is that if you have a 2 by 2 matrix, A, B, C, D, you can use this shortcut to find the inverse. Here, the matrix A, -1, 2, -2, -1, we're looking for the inverse of that. It's a 2 by 2, so we can use the shortcut. What does the shortcut say? Interchange the two entries on the main diagonal, right? So interchange these two, well, it's the same thing. And then the off diagonal, just take negative of those entries. So -2, -2, which is +2. The whole thing divided by AD minus BC, the product, this minus that. So 1 minus -4, or 1 plus 4 is 5. So here's the inverse. Here's the inverse of that. We can check, right? We can check if you multiply this by, what do we get? 1 plus 4 is 5. -2 plus 2 is 0. -2 plus 2 is 0. And 4 plus 1 is 5 again, which is easily seen to be the identity. We know we're right. So here's the inverse. And your unknown, xy, is A inverse B, or in this case, 1/5 -1 minus 2, 2 minus 1 times 1520. What do we get? Minus 15 plus 40 is 25. And 30 minus 20 is 10. Or 5 and 2. In other words, x equals 5, y equals 2. Would you want to distribute the 1/5 value into the matrix? Yes, yes you would. But I like to not play around with fractions. So if you leave it outside, the fraction is completely out and you're good to go. I mean, if the question was asking for a matrix, which is its inverse, then you would probably want to distribute it throughout, yes. What exactly does the B represent here? Well, B was this thing, right? This matrix of coefficients, matrix of constants, if you will, in this development here. So, as Victoria suggests, B is 1520. So I'm suggesting that the solution x equals 5, y equals 2. Let's check. 5 plus 4, no, minus 5 plus 4 is not 15. We're in trouble. We're in big, big, big trouble. What has happened here? This is completely wrong. This is what happened. Minus 15, minus 40. This is actually, I don't know how I got 25. This is minus 55. So this should be minus 11. Have other mistakes been made? No. So this should be minus 11 and not 5. Let's try that again. 11 plus 4 is 15, looking good. 22 minus 2 is 20. There you go. There you go. And I mean, this shows the importance of checking your answer, right? Because we had made a terrible mistake. Questions here? Do we want to do another one of these? Or we're comfortable with that? One more, perhaps? Let's do one more. It's good practice to make use of the 2x2 inverse, right? Instead of working it out the long way. Right, again, the idea being that we can rewrite this in this form. So if we denote A by this matrix, then we have A times xy is 1 minus 1. So xy is A inverse times 1 minus 1. How do you get the inverse? How do you get from the inverse 2xy? Well, exactly this way, right? I mean, this is really A times xy equals that. So multiply the whole equation by A inverse on the left. A inverse times A is going to be the identity. The identity times xy is just xy. And on the right, you have A inverse times 1 minus 1. So if A is that, A inverse Using the shortcut, 1 over AD minus BC, so 27 minus 30 is minus 3. Interchange these two, and negative of those. There we go. So xy is the inverse times 1 minus 1. What do we get? 9 minus 6 is 3. 5 minus 3 is 2. So negative 1 and negative 2/3. So x is negative 1, y is negative 2/3. Let's check, is this right? Minus 3 plus 12 over 3, which is 4. Minus 3 plus 4 is 1. Looking good. 5 minus 18 over 3, which is 6. So 5 minus 6 is minus 1. There it is. Very good. There's some nice little claims which we can prove using the inverse and using the uniqueness of the inverse that we showed last time. Claim if A is invertible and C is a real number not equal to 0, then C times A is invertible. And its inverse, the inverse of C times A, is 1 over C times A inverse. Here we're using the shortcut. C is any real number that is not 0. Here we're using the shortcut. We said that if A is any 2 by 2 matrix, its inverse is 1 over AD minus BC times D negative B negative C. Assuming this denominator is not 0. Right, so you switch these two things. You switch the main diagonal and you take a negative of the remaining two entries. So switch the main diagonal and the negative of these entries. The whole thing divided by AD minus BC. Everybody with us here? So here's my claim. If A is invertible and you take a non-zero number, then C times A is invertible. And its inverse is 1 over C times A inverse. Let's prove it. Let's prove this. What do we need to prove? Take a step back. I'm suggesting that the inverse of CA is this. So all we need to prove is that CA times this is the identity. Because if that's true, then this has to be the inverse of CA. If you multiply these two things together, what happens? Well, these are constants, so you can pull all of these things out. So this is C times 1 over C times A inverse. And now if you group these two things together, C times 1 over C is just 1. A times A inverse is just the identity. And the identity times 1 is just the identity. And that's it. So this matrix is the inverse of that one. This matrix is the inverse of that one. Convinced? How can we tell if the inverse exists? An excellent question. And as far as we're concerned, the only way we can tell if an inverse exists is if you can row reduce it to the identity. Unless you're using the 2x2 shortcut, which tells us that AD minus BC should be different from 0. Let's take another example here. All right. Consider this. Suppose you have two matrices, two square matrices of the same size, which are both invertible. My claim is that the product is also invertible. And the inverse of the product is the product of the inverses in the reverse order. Let's prove it. What do we need to prove? All we need to prove is that if you multiply this by the matrix AB, you get the identity. Kessia is asking if we have to row reduce first to see if the matrix is invertible. That's the only, in this class, that's the only technique we have. Unless, of course, the question tells you that it's invertible, right? And so here we have both A and B to be invertible matrices themselves. So observe what happens if we multiply these two things together, right? I mean, as long as you respect the order, you can group as you want. So let's group B times B inverse. What does that give us? That gives us the identity. And the identity times any matrix is that matrix back. And A times A inverse is the identity. Exactly what we wanted to prove. This matrix times this matrix gives you the identity. Of course, if you do the other way around, right? A inverse B inverse times AB, the same thing's going to happen, right? You're going to group these, you'll get the identity. The identity times B is just B, and then B inverse times B is the identity as well. Similar. You didn't need to do both ways because we saw last time that our REF stands for reduced row echelon form, right? You know what that means. We gave a lengthy definition. Well, let's not break up every single word, but rather it's the phrase reduced row echelon form which is important. What does reduced row echelon form mean? It means, I mean, there were four conditions, right? The first non-zero entry in each row is a 1, called the leading one. The leading one is the only non-zero entry in its column. Leading ones move to the right as you go down the matrix, and rows of zeros, if any, are at the bottom. If your matrix satisfies these four conditions, then it is in reduced row echelon form. Reduced row echelon form is the simplest form the matrix can have. Shall we do an example? Suppose that you had row reduced. Suppose you had row reduced your augmented matrix to this situation. My first question to you is it in reduced row echelon form? We're not going to the inverse. Why does the inverse turn rows into columns and columns into rows? Let's not. I mean, we never said that. We never said that. But rather, let's take an example of reduced row echelon form. My question to you is this matrix in reduced row echelon form? Let's go through the four conditions. The first non-zero entry in each row is a 1, called the leading one. The leading one is the only non-zero entry in its column. Now, those two conditions are met. Leading ones move to the right as you go down the matrix. This is to the right of that one. Well, that condition is met as well. Rows of zeros, if any, are at the bottom. There are no rows of zeros, so that statement is vacuous. And there it is. This is in reduced row echelon form. I don't know what you mean about flipping. There's no flipping here. This matrix is in reduced row echelon form. It satisfies the four conditions. We're good to go. This is the simplest form the matrix can have. So from then on, we should be able to read off the solution. The diagonal does not have to line up. The leading ones must be to the right of the preceding one as you go down the matrix. This one is to the right of that one. That's all that's important. So it doesn't have to be directly to the right. It has to be to the right. Of course, everybody is welcome to come and watch. So this is in reduced row echelon form. Now suppose, we didn't have an actual system of equations that led to this, but suppose this was a column reserved for x, y, z, and w. This is in reduced row echelon form. What is the solution? This is the simplest form the matrix can take. So we should be able to read off the solution. What is the solution? You tell me. Remember, what had we suggested? Variables that do not have leading ones get replaced with parameters. Y does not have a leading one. W does not have a leading one. Y and W get replaced with parameters. Ben has suggested T, but they don't have to be the same parameter. In fact, they should be different parameters, right? Y equals S, W equals T. Two parameters, as Annie suggests. Absolutely. And then, from this last one here, we see that Z plus W is equal to 4. So Z is equal to 4 minus W, but W is T. And in the first one, X plus Y plus 2W is equal to 3. Or X is equal to 3 minus Y, which is S, minus 2W, and W is T. This is the solution. Questions? Anyone? Can we group any matrices of any size if we follow the order? As long as the multiplication and or addition is defined, yes. Y minus, well, you know you bring everything to the other side, right? You know that this last row here is really saying Z plus W is equal to 4. All right. Let me tie up some loose ends as far as matrix multiplication, addition, and inverses are concerned. We have just proven here that if you have two matrices that are invertible, and of the same size, then their product is invertible, and the inverse of the product is the product of the inverses in the reverse order. This is not true for addition. If you take two matrices which are invertible, and you add them together, Eric, when we were row reducing, we said variables that don't have leading ones get replaced with parameters. Here, y does not have a leading one. The leading ones are underlined here. X has a leading one, z has a leading one. Y does not have a leading one, w does not have a leading one. So y and w get replaced with parameters. Max is asking if we're allowed to assume there are two rows of all zeros. There's no need for that. No need. Well, Eric, I mean, if you understood this last line, then the first one is the same thing. Right? What does the first one say? The first one is saying 1x plus 1y plus 2w is equal to 3. Here, what I want to show you, right? Here, if you have two matrices that are invertible, then the product is invertible. But if you have two matrices which are invertible, their sum may not be invertible, right? What is the sum here? This matrix plus this matrix is easily seen to be the zero matrix, right? And this is a 2 by 2 matrix, so you can find the inverse using the shortcut. It's very easy to see that this matrix is its own inverse. And here, you've got a 2 by 2 matrix. You can use the shortcut. You can also show that this is its own inverse. I'm not sure what you mean by pictures there, Eric. There are no pictures here. Yes, well, one line represents one variable. Again, it's a questionable interpretation. Rather, what does this line actually say? And that's what it says there. So if you add these two invertible matrices, you get the zero matrix, which is not invertible, right? Because AD minus BC is equal to 0. So this is not an invertible matrix. Also, if you multiply this, right, if you're looking for an inverse, if you multiply the zero matrix by any other matrix, what are you going to get? First row times first column, it's easy to see that you get zeros everywhere. So the zero matrix times any matrix gives you the zero matrix back. You're never going to be able to get the identity. So the zero matrix is not invertible. There you have it. Also, right, I mean, the zero matrix really behaves like the number 0, right? When you multiply a matrix times this matrix made up entirely of zeros, you get matrix made up entirely of zeros. Again, if you add them together, you get the original matrix back. So a matrix made up entirely of zeros is known as the zero matrix. Questions here? I feel like we haven't really done anything today, and we're already running out of time. Let me point one more thing out. In the real numbers, if you have a product equal to 0, then one of the factors has to be 0. We use that all the time in calculus. Then A equals 0 or B equals 0. One of the factors has to be 0. By the end of today's lecture, we will have done everything for web work 1. So if you have a product, if two numbers multiply together to give you 0, one of the factors has to be 0. This is in the real numbers. This is not the case. This is not the case for matrices. Let's observe that you can take two non-zero matrices and multiply them together to get the zero matrix. Consider these two matrices. First of all, each of these is not the zero matrix because you have a non-zero entry. And well, Brendan, I think this is a counterexample. And what happens if you do the multiplication? This times that, well, that's 0. This times that, that's 0 again. And 0, 0. These two matrices together multiply. These two non-zero matrices multiply to give you 0. Now, somebody had pointed out that assignment 1, web work 1, introduces something we haven't seen yet. So let me introduce it right now. Definition. Given an m by n matrix A, we define the transpose. Denoted a transpose to be the n by M matrix. Right, so observe, we started out with an M by N, and now it's the opposite. To be the N by M matrix whose rows are the columns. Of A. Let's take an example. Suppose that we have this matrix A. What is A transpose? A transpose is the matrix whose rows are the columns of A. So the original columns, column 1, 2, 3, become row 1, row 2, row 3. You rewrite the columns as rows, or equivalently, the rows as columns. So there you have it. The transpose, you rewrite the rows as columns or the columns as rows, however you wish to view it. Observe that if you take the transpose of this matrix, right, we write the columns as rows. So first column will become the first row. Second column will become the second row. And you're back to your original matrix. The transpose of the transpose is the original matrix. What's the point of this? Well, certainly one point is because it appears on the first web work. So that's an obvious reason to learn that material. Secondly, the transpose has some nice properties which are very similar to the inverse. Claim the transpose of a product is the product of the transposes in the reverse order. What textbook sections did we cover? I feel we didn't cover anything new. We're still on matrix inverses. Yeah, so we're still in last week's section. So here's my claim. The transpose of a product is the product of the transposes in the reverse order. I won't prove it, but let's think about why that's true. To evaluate an entry here, what do? You're going to take a row of A, so row of A times a column of B. right? That's how multiplication works. You take a row and you multiply by a column. When you take the transpose, columns become rows. And rows become columns. And to multiply these two things together, you take a row in here and you multiply by a column in there. That's essentially the proof. How are we doing here? Questions? All right. So what's coming up? I had prepared some material for today. We didn't get to it. No worries. Let me tell you what's coming up. By giving you an example, you've all heard of the Alberta oil sands, right? I mean, that process of extracting oil from the sand is a very polluting process and very costly in energy as well. It's, I mean, maybe the process has gotten a bit better, but in the beginning, in order to extract 1 barrel of oil, you needed, or the whole process consumed 1/3 of a barrel. So in order to produce 1 barrel, of oil, this consumed 1/3 of a barrel. So here's the question. Suppose you wanted to meet a demand of 100 barrels. Suppose you want a net output of 100 barrels. How many barrels must you produce? Well, I mean, I think you can probably work that out by trial and error, right? If you produce 150 barrels, 1/3 of this production gets eaten up in the process. 1/3 of 150 is 50, and 150 minus the 50 gives you the 100 barrel output that you wanted. And that's all well and good. Of course, there's a mathematical principle behind that, and you can work that out very easily. There's no guesswork here. But what I want to bring your attention to is, what if we scaled this up? Right? 1 barrel of oil consumes 1/3 of a barrel of oil in the production process. But of course, you understand that there's a lot more going on here, right? You need workers to extract that oil. These workers must be fed. These workers need food. To produce the food, you need some oil for the machinery in the fields, for the workers to get around. But the workers need more than food, right? They need housing, they need clothing, they need this and that. In the production of clothing and housing, you need oil. But these workers that are producing houses and clothing and all that, they need houses. They need to be fed. They need oil. They need clothing. And same with the manufacturer. Same with those manufacturing workers, right? They need to be fed and clothed and housed and this and that. So everything is all intertwined. The production of 1 barrel of oil consumes 1/3 of a barrel of oil, but it also consumes calories. It also consumes clothing, manufactured goods. It also consumes a bunch of things that the workers themselves are consuming. So you end up with a bunch of intertwined, interconnected equations. And the question is, how do you make sense of all of this? It quickly becomes overwhelming. How do you keep track of that? And that's what we're going to see on Thursday via the beautiful process devised by Leontief, for which you won a Nobel Prize. We'll see that on Thursday. Thank you all for coming. Britton had a small question there. Can you multiply any square matrices in any order? I mean, if you mean AB versus BA, the answer is no, even if they're square. If you mean grouping like this, as long as you respect the order, right? As long as A is on the right of BC, then yes. So matrix multiplication is not commutative, but it is associative. So that's where we're headed on Thursday. Thank you all for coming. And I will see you then. You guys have a good one. See you Thursday.